Hello, welcome to the Discrete Math site. Today I'm going to cover strong induction, and that's part 3 of mathematical induction. Start with this example. We claim that if you have a whole bunch of 4-cent stamps and 5-cent stamps, then you can make any postage of 12 cents or more. So if you have a 4-cent postage, obviously you can use one of these stamps and no stamps, no 5-cent stamps. 5 is 0 and 1. 6, you can't really solve it because you only have 4-cent stamps and 5-cent stamps, and you can make 6 out of those. 7, it doesn't work either. 8, it works because that's 2 times 4. 9, it works. That's 4 plus 5. 10, it works. 2 times 5. 11, it doesn't work. Now let's see what happens starting from 12. 12, you have 3 times 4 is 12. 13, you have 2 times 4, 8 plus 5 is 13. 14 is 4 plus 10. 15 is 3 times 5, 15. Now, for 16, I really don't need to think too much about it because I know I can solve it for 12. Then all what I have to do is take this and add 1 to it. Then I will have 4-cent stamps to get 16. 17, that's 13 plus 4. 18, that is 14 plus 4. And 19, that is 15 plus 4. So you see what's happening here is this here is the solution. Sorry about that. This here is 12 plus 4. This here is 13 plus 4. 14 plus 4. 19 plus 4. We're only adding 4 here. So the principle of mathematical induction to prove for all n greater or equal than 1 Pn is true, you can prove P1 to be true and then prove Pn implies Pn plus 1 is true. That's what we have done in part 1 and part 2 of this series. So, and this is sometimes referred to as weak induction. The strong induction, it's you prove P1 is true, and then you prove P1 and P2 and Pn all implies Pn plus 1 is true. And those are really equivalent, but sometimes your knowledge at n does not help you to prove Pn plus 1. You have to go back before that to see, pick up some between P1 and Pn, or some of them, 2 of them or more, to prove that all of this implies Pn plus 1. Then you can prove Pn plus 1 is true. Let's take a few examples here. The first classical example is prime factorization. And in prime factorization, we say that any integer n greater or equal than 2 can be written as the product of primes. So to do that, we're going to set up this proposition. So let's Pn be the proposition that n can be written as the product of primes. That's what we're trying to prove. So we're going to use strong induction. Basis step, let's prove P2 is true, which is really true because 2 is a prime number. Now here's how you set up the inductive step. You suppose Pk is true for all integer scale between 2 and n. In other words, you suppose P2 is true, P3 is true, Pn is true, and now you have to prove Pn plus 1 is true. And here we have two cases. If n plus 1 is prime, then there's nothing really to prove because it's already written as a prime number, as a product of not prime numbers. Now, if n plus 1 is composite, then n plus 1 is the product of two integers, a, b. Each one of those, a and b, are less than or equal to than n. So you use the inductive step hypothesis to say that, okay, a can be written as product of primes, and b can be written also as a product of primes. Then when you multiply them, you get a product of primes. Here's another example. Show that every positive integer n can be written as a sum of distinct powers of 2. That is called the, that's a binary representations actually. So here's how you set it up. You say let Pn be the proposition that n can be written as a sum of distinct powers of 2. Basis step, P1 is true because P1 can be written as 2 to the power 0. 1 is equal to the power 0. Now, inductive step, that's really important how you set it up. You suppose Pk is true for all integers k between 1 and n, meaning that 1, 2, 3, up to n can be written as sum of powers of 2. Now you have to prove that n plus 1 can be written as power of, as a sum of powers of 2. Two cases, if n plus 1 is odd, then n is even. All what you have to do is add to the sum for n 1, which is 2 to the power 0, and we're done. When case 2, if n plus 1 is even, now I can write n plus 1 equals n plus 1 over 2 times 2. This here is also an integer because n plus 1 is even. So when you take a number even divide by 2, still be an integer. Now, we know from the inductive step here, we know that I can write this here as sum of distinct powers of 2. Then all what I have to do is take each term, each exponent, and increase each exponent by 1, and we get the answer because I'm timing it by 2. Timesing it by 2. Here's the last example. Jacobsthal numbers, and I hope I'm pronouncing his name correctly. These are the definition of these numbers. Jn is Jn minus 1 plus twice Jn minus 2. J1 is 1 and J2 is 1. So the way you generate these numbers, all what you have to do is look at it like this. Okay, start this is 1, 1, and then it says here every term is the previous plus twice the one that is before it. So now here I'm going to get the previous plus 2, this gets 3. And here you get 3 plus 2, 5. Here you get 5 plus 6, 11, and so on and so forth. So this one here is J1, J2, J3, J4, J5. So each term is the previous term plus twice the term before it. So what we need to prove is Jn is 2 to the power n minus 1 to the power n over 3. If I do that, then I can find j at any number immediately. If I can prove this, then j of 10, then 10 to the power 10 minus 1 to the power 10 over 3. While here, if you want to find J10, you need to find J1 up to J9 in order to be able to find J10. So basis step, n is equal to 1. J1, we replace n by 1. Excuse me. And we get 1, which is true. Now, inductive step, we suppose that Jk is equal to 2 to the power k minus 1 to the power k over 3 for all k between 1 and n. And we need to prove Jn plus 1 equals 2 to the power n plus 1 minus 1 to the power n plus 1 over 3. Now, look at this one here. We're going to be using this. We're going to be using it. So now we go to the proof. This is the numbers, this definition of Jacobsthal numbers. Now, what I need to do is I'm going to replace this by this using the inductive step, the inductive hypothesis. And this is replaced here. Going forward is just kind of doing the math. So common denominator, this one stays the same. 2 times 2 to the power n minus 1 is 2 to the power n. This is times minus 2. Now this one here, consider this minus 1. When I multiply it by this, I get minus 1 to the power n plus 1. And then here, what I did is I added this, which is negative 1 to the power 2, which is 1. The reason being is I want to make this power, all of them, I want to make it n plus 1. So you get this. Now you notice that this term here is the same as here. 1 and minus 2 is minus, and you get exactly the answer that you want. And this concludes part 3 of mathematical induction. Thank you very much, and see you soon.